Hello and welcome, my fellow path integrator. Today's integral I would like to solve with the residue theorem. Some of you might already know this integral because I've solved it in a previous video with more conservative integration techniques, but today I thought I would like to use one of the most powerful techniques that physicists use to integrate, and it is using the residue theorem. So how are we going to do it? So the residue theorem tells us that we can integrate an improper integral from minus infinity to plus infinity easily by just counting the residuals of the singularities inside of the definition area of the definition set of the function. So in our case, what we have to do is we have to find the singularities of the function in the integral, of the integrand itself. So what we need to find is we need to find the solutions for this equation. X to the power of 4 plus 4 is equal to 0. And this, of course, means that x to the power of 4 is equal to minus 4. So in order to get the solutions to those roots, the 4 solutions, we will have to take the complex roots of this, or let's call it 0, 1, 2, 3. So we start at 0, 1, 2, 3. You will see in a second why I start at 0. So the solutions would be the fourth square root of minus 4. So there will be 4 solutions. How are we going to do it? We're going to apply Euler's beautiful formula, which is that a complex number is equal to the radius times the function, the exponential function, to the power of I times the angle phi. And we can write this also as r times cosine of phi plus ir times sine of phi. So this means that minus 4 can be written as 4 times the cosine of, and then we choose the angle pi because cosine at pi is equal to minus 1, and then we choose the angle pi also because the sine of pi is equal to 0. So we have plus I times the sine of pi, and this can actually be applied to any square root of a negative number. So all we have to do, it doesn't matter if we want to take the square root of minus 104, for example, we just have to write it as 104 times the cosine of pi plus I times the sine of pi. So this is just something that I wanted to include here. This is a basic formula that we can just apply all the time. So let's shift that up here. All right, so now we have that. Now how do we take the square root? There's the formula that we can apply is that the fourth square root of minus 4 is the fourth square root of 4 times, and now we take the cosine of the angle pi plus 2k pi divided by 4. So the amount of square roots that we, the amount of roots that we want to take, sorry for saying square root, and then plus I times the sine, and then we have the exact same argument as for the cosine. So we divide that by 4. And the interesting thing now is that k starts at 0 and then goes to 1, 2, 3. Because if we plug in k equals 0, we also get a solution to the fourth root of minus 4. And the same for k1, k being 2, and k being 3. So all we have to do now to get the solutions of the 4 roots that we need, we all just have to plug in k, the values for k. So let's start with the first one. So let's say set 0 or set not is equal to the fourth root of 4 is just the square root of 2, and then we have times the cosine of pi over 4 because k is equal to 0 plus I of sine of pi over 4. All right, so the cosine of pi over 4 is 1 over square root of 2, so we have square root of 2 over square root of 2, and this just gives us 1. And then we have plus sine of pi over 4 is also the square root of 2, so we have I times the square root of 2 over the square root of 2, and the square root of 2 is obviously just 1. So Similarly, we'll do it for z1, so we have the square root of 2 times cosine of, and now we have pi plus k equals 1, so pi plus 2 pi, so 3 pi, so we have 3/4 of pi, and the same argument is in the sign, so we have 3/4 of pi here, and 3/4 of the cosine of 3/4 of pi is -1, -1 over square root of 2, but we have minus square root of 2 over square root of 2, and this just gives us 1. And then we have the sine of 3/4 pi. This is just 1 over square root of 2, and this cancels out with the square root of 2, so we are staying with a 1 here, with an I here. All right, z2 is the square root of 2, then we have the cosine of 5/4 pi, and the same argument we have for the sine, and here we get in a similar manner -1 minus I, and the last root is the square root of 2 times the cosine of 7/4 pi plus I times sine of 7/4 times pi, and here we have the cosine of 7/4 of pi is positive again. 1 over square root of 2 cancels each other out with the square root of 2, but the sine of 7/4 times pi is negative, so here we have minus I. Okay, now we have the singularities. Now we need to calculate the residues of those singularities, but only of those singularities which have an imaginary part bigger than 0. So what is important for our residues is that the imaginary part of the singularity is bigger than 0. And this is the case for z0 or z0, and this is the case for z1. The other ones, they don't have a positive imaginary part, so we cannot use them. So what are we going to do now? Now we have to calculate the residues for our function in those singularities. So let's recall what our function is. Our function f of x is 1 divided by x to the power of 4 plus 4. So what we have to do now is we need to know how to calculate the residue of a singularity in a function like this. And this is quite simple for rational functions, because the residue in a singularity set k of a function f is just, if f is like a function, let's write it here, wait a second. So f of x is a polynomial divided by another polynomial, so a rational function. So the residue of this function in a singularity set k is just the numerator polynomial at this singularity divided, and now comes the special part, the derivative of the denominator polynomial evaluated at the singularity. So it's quite simple. We just have to calculate the derivative of this denominator here. So what we get is that in our case we have residue of, let's say, set naught is our first residue of set naught of the function f is p of z naught is just 1 divided by the derivative of the function here is just 3 times x, sorry, not 3, 4 times x to the power of 3. The 4 just drops because it's a constant, so here we have 1 divided by 4 set 0 to the power of 3. And the same is for the residue of the singularity set 1. It's just 1 divided by 4 set 1 to the power of 3. Wow. Okay. Now we have to calculate those residues. So this is a little bit of an exercise how to handle complex numbers. So this is quite easy. So first of all, we plug in z0 or z0 is, let's look here, 1 plus I. So let's plug the 1 plus I in. So let's do it in 2 columns. So we have this, we have 1 divided by 4 times, and then we plug in 1 plus I to the power of 3. All right, let's keep on going. So we have 1 divided by 4 times 1 plus I squared times 1 plus I. I like to extract it this way. Then we have 1 divided by 4 times 1 plus I squared. This we can extract with the binomial formula. This gives us 1 plus 2i minus 1. So this, of course, is just 2i. So we have here times 2i. And then we remain with a 1 plus I. So let's put that line down. So here we keep on going. We have 1 divided by 8i times 1 plus I. And this just gives us 1 divided by minus 8 plus 8i. All right. So this is just, here we can write this as 8i minus 8. And then we use the third binomial formula to get an expression in the form x plus iy. So because now we have the I in the denominator and it's quite hard to know what is the real part and what is the imaginary part. So what we do is we say this is 1 divided by 8i minus 8 times 8i plus 8 divided by 8i plus 8. And this in the end gives us 8i plus 8 divided by, and here we have minus 128. And this eventually gives us 1, so minus 1 plus I divided by 16. And in a similar manner, we're going to do that for the second residue, which is here 1 divided by 4 times, and our second singularity is minus 1 plus I. So minus 1 plus I to the power of 3. And similar, we have 4 times minus 1 plus I to the power of 2 times 1 plus I. And then we keep on doing the maths. I'll just spare it to you here because it's just the same as before. All you have to do is take care for the signs or for the minus and plus signs. You can get very confused with that. Anyway, so the final result is 1 minus I divided by 16. So those are our residues. So our first residue of Z0 of the function f is minus 1 plus I divided by 16. And the second residue that we needed was 1 minus I divided by 16. So let's recall our formula to calculate the integral. So we have minus infinity to plus infinity for our improper integral, 1 divided by 4 plus x to the power of 4 dx. And this is equal to 2 pi I times the sum of all of the residues times the sum of all of the residues of the function with the imaginary part of the singularity corresponding to the residue being greater than 0. So what we have to do now is we just have to sum those two residues up and multiply the sum by 2 pi I. So what we get is 2 pi I times, and then we have minus 1 plus I divided by 16 plus 1 minus I divided by 16. So we have minus 1 plus 1, those two cancel each other out. Then we have minus I, this is minus 2I. So we have 2 pi I divided by 16, 2 pi I divided by 16 times minus 2I. All right, this is also quite simple because 2 pi divided by 16, this just gives us pi over 8. Then we have the 2 here, so the pi over 8 turns into a pi over 4. And then we have minus I times I squared. I squared is just minus 1, so we have minus 1 times minus 1 equals 1, and this is our final result, pi quarters. Amazing. So I just love the residue theorem so much because you just completely avoid calculating antiderivatives, but it only works for improper integrals. Also, the proof is quite beautiful on how to use the residue theorem on improper integrals. So I think I'll do a video on that one, so stay tuned. Yeah, we're at the end. Very much thank you for staying with me. I hope you had fun. I hope you could learn something today. And you know it, just subscribe to the channel, maybe leave a like, maybe comment. Now you have seen how to do cool integrals. I'm sorry, I never know what to say in the end. See you in the next video. Bye!